Hi all, welcome to Mr. Cooper's YouTube channel. Thanks for watching. Give me a big thumbs up. Don't forget to subscribe. I've been given a kind of speech by my 6-year-old to say. So I'm trying to go through feedback for exams and things like that to kind of help you out. What I will do in future is go through the paper live. But on this one, I haven't got any in front of me. I want to kind of show you, give you the answers. So I'll go through the mark scheme and talk it through. I've got it on my screen in front of me, so if you think I'm looking kind of through the camera, it's the best I can do at the minute. So we'll go from there. So this is our Feb Mock that you've just done. It's a 50-minute paper, straightforward for a start. We've got some multiple choice questions. So which class of material does titanium and its alloys belong to? That's just a 1-mark question, quite straightforward on that one. So the answer there is titanium is non-ferrous. It's not got the word iron or steel in, so therefore it's non-ferrous. And its alloys are also in that. Which class of materials does melamine formaldehyde belong to? Well, hopefully you remember that that's a thermosetting polymer. Okay, so it's not affected by heat. It's used for work surfaces, that kind of thing. Young's modulus is a measure of a material's ability to withstand changes to its length. Okay, so this is Young's modulus, where we plot that curve that we showed. It goes up, it kind of wobbles for a bit, and then goes kind of on a curve, and then the material snaps and it drops straight down again. So Young's modulus kind of talks about the calculation of the length of extension. Okay, so from measuring its original length to its extended length, if you like. And then we go on to the questions. I'm just pulling my mark scheme up now so I can go through this with you. State 2 common materials that component A, the outer shell of the motorcycle helmet, is commonly manufactured from. For each, give a reason why it's suitable. So in the mark scheme, it talks about accepting polycarbonate thermoplastic. So polycarbonate is the stuff that we use for bush shelters, that kind of thing. So it's an impact resistant plastic. GRP or fiberglass, again lightweight, impact resistant. Kevlar, another kind of smart material, modern material. Carbon fibre reinforced plastic, CFRP, carbon fibre. Or any other suitable answer. So I could take ABS, impact resistant again. It does say though, don't accept. It always makes me laugh, these ones. Steel, iron, ceramics, silver, bizarre one, or concrete. Why you'd consider making a helmet from concrete, I'm not sure, but I like how it does tell us to not accept that one. I'm just moving my cameras around slightly so I can see my screen. I've got the dog asleep in the background on the bed, so if he rears his head up, I do apologise. So that's 1 mark each for any of the above, 2 marks maximum. So it's coming up with something and then accepting it. So we're looking for low density, lightweight, tough, forms of supply, how it comes kind of in suitable forms of supply, ease of manufacture, aesthetic quality, so it looks nice, readily available, corrosion resistant, water resistant, strong. I mean, strong's a really weak one for me. I'd be looking for you to kind of quantify that one. Explain what is meant by the term smart material. A lot of you really struggled with this one. Smart materials have properties that react to changes in their environment. So you could be looking at photochromic things that change colour with light, things that change colour with water, with heat, anything like that. It means that one of their properties can be changed by an external condition, such as temperature, light, pressure, or electricity. I've seen some quite funky kind of glass that in houses being used at the minute, that you flick a switch, it sends electrical charge through the glass and makes it go dim. So you don't need any curtains, for example, in this house. Change is reversible and can be repeated many times. A wide range of different smart materials, each offer different properties that can be changed. So give me 1 mark given for react to changes or something like that, so changes to an external stimulus. 1 mark for environmental or external condition. 1 mark for properties that can be changed. 1 mark for reversible, 1 mark for repeatable. Any other suitable response along those kind of lines gives you a maximum of 4 marks. Okay, so it's that idea that it reacts to a certain stimulus, it reacts to its environment. So, for example, my glasses, if they were reactor lights, they would dim in the bright sunshine, so it acts like sunglasses. Okay, and as soon as I come back inside into the darker light, that tint goes away and it goes back to normal glasses. Okay. Name 2 smart materials for each. Describe one typical application. So smart materials accept shape memory alloys, so glasses that you can fold up and then spring back. Piezoelectric materials, quantum tunneling composites, your QTC, electroluminescent materials, thermochromic materials to do with heat, photochromic to do with light. Okay, so stuff that changes. And think about the applications there that we've got. So smart material applications, we can look at SMAs used for spectacle frames, used as triggers to start the sprinklers in fire alarm systems, controllers for hot water valves in showers or coffee machines. Their shape can be returned to its original shape by heating above the critical temperatures. We heat them up and it changes back again. Piezoelectric materials are used for contact sensors for alarm systems in microphones and headphones. Their shape is changed by electrical current, so we get that kind of pounding of the electrical current. QTC can be used to make membrane switches like these on mobile phones, pressure sensors, speed controllers, as its electrical resistance is changed with pressure. Bit of a deep one, that one. Electroluminescent materials give out light when an electric current is applied to them. Among many possible applications are safety signs and clothing for use at night. So think about glow in the dark stuff. Safety lights, that kind of thing that will glow, kind of emit a glow when it's darker. I used to get like alarm clocks with those on. Your watches might have little marks on the faces if you've got like a Mickey Mouse's big hand and little hand on your watch. Thermochromic materials used on contact thermometers made from plastic strips and test strips on the side of batteries. You used it as food packaging materials that show you when the product they contain is cooked to the right temperature. So their colour changes with temperature. So a duck that a child would have in a bath, for example, could have a thermometer on it. Tells you what the temperature is. Very easy to do. Photochromic materials used for security markers that can only be seen in ultraviolet light. Their colour changes with the incident light. 1 mark for an application, 1 mark for a detailed response. So 2 marks maximum there. So a table of materials. Copper is non-ferrous, used for electrical wires. High carbon steel is a ferrous metal. Bearings, knives, saws, blades, springs, gears, cold chisels, wrenches, pneumatic drill bits, wheels for railway services, wire for structural work, shear blades, hacksaws, anything like that. Borosilicate glass. Now this was one that my group didn't get very well at all. That's a ceramic, or an engineering ceramic is its correct title. 3D printer beds, so we've got one of those at the back of my room that's got a glass bed on. The white box, the automaker's got a borosilicate glass bed. Pyrex jugs. Pyrex is the trade name, borosilicate glass is the material name. Pyrex is the company that makes that, but your parents or you might have like a glass jar or glass cookware. That's borosilicate glass. Beakers and test tubes in science, anything that requires resistance to thermal shock. So anything that's going to get hot then cold again. So to do with cooking, to do with test tubes in science, you're going to heat it with a Bunsen burner to get it to, I don't know, explode the material, whatever we're doing, or mixing it. Photochromic materials, they're smart materials. They change in relation to their external stimulus. Sunglasses, visors, etc. Novelty plastic items such as toys, combs, beads, drinking straws, cups, spoons, drink bottles. Security printing, for example, as anti-counterfeit markers on banknotes, and documents such as passports, fishing lines, and light-driven switches. Okay, so anything that kind of changes colour, changes to do with the light, photo to do with light. Okay. Let's have a look. I haven't got this one. Bear with me a second while I just put the question paper up. So the next question, it's not got on the mark scheme for me. Okay, yeah. Figure 1.1 shows a roller blind fitted to a window. The blind is shown in the raised position, but it can be lowered to cover the window. A smart roller blind is being developed as part of a smart home technology system. The smart roller blind will raise or lower automatically under the control of the smart home technology system. Just a bit of context there, really. It means nothing other than it wants to be done electrically or electronically. Okay, so it's just a roller blind it's going to wind up and it's going to roll back down again, a bit like the one I've got in the background you can see behind me. That's not electric, by the way, I'm not that posh. Figure 1.2 shows a prototype roller blind mechanism. So it's got a worm and worm wheel going on here. The worm is like a round bar that's got a thread on it, like a screw, and then the worm gear meshes into that and rolls along. This turns round, just constantly rolls around, allowing that to roll over the top of it. The roller diameter is 35mm, the blind. A DC motor drives the roller through a worm drive system. Explain one functional feature of a worm drive system that makes it useful in the roller blind mechanism shown in figure 1.2. Then calculate the circumference to the nearest millimetre. Okay, it gives us the millimetre symbol. It's asking for the nearest millimetre. So let's have a look at what the mark scheme says for us. So the input worm drive can scan the output gear but not vice versa, which means that the blind cannot fall under its own weight. So it's giving it constant drive, constant feed if you like, when the motor's not running. The input worm screw can drive the output wheel but not vice versa. So it can't fall under its own weight, like it's just said. It's strange, it says it twice. A large gear ratio provides slow rotation, steady controlled movement. You don't want this blind shooting up and down. Okay, you want a nice gentle raise up and raise down. Enabling the user to stop the blind at a desired position. So it's going to go up gently, you can stop it exactly where you want it to. Any other valid suggestion? A large gear ratio can be achieved in one stage, which allows for a compact gearbox size. So you don't want this gearbox being massive and add into the kind of aesthetics of your roller blind. You want it kind of hidden within the body of it. Mechanism's quiet in operation, which is beneficial in a home environment. You don't want this thing whirring away, for example. Specific reference to the context in the question is needed for marks to be awarded. So we're talking about it being in the home situation, in the bedroom, for example. So it's got to have that kind of noise relation, some kind of acknowledgement that we don't want to affect the look of it. Don't accept the drive is transferred through 90 degrees unless it's clearly justified why it's used useful in a roller blind system. So we don't need to know about that because it's not really relevant. The circumference then of the roller diameter, circumference is equal to pi times diameter, or 2 pi r. Okay, so you've got to put the equation down for 1 mark. So it's the circumference equals pi 3.142 times 35, which is the diameter, which gives us 110 to the nearest millimetre. Okay, so that's 1 again. So 1 for the equation. Make sure you always write your equation. There's always a mark for putting that in. Put your numbers in. Give me an answer. Okay, normally more than 2 marks, but that's all they're after for this one. Quite a simple little calculation there. Go back to my question paper again. During testing the prototype system, a design engineer notices the speed at which the blind rises does not stay constant but gradually increases throughout the raising cycle. So as it raises up, it gradually gets faster. Well, why is that? The roller blind, study the roller blind mechanism, mechanical drive system in 1.2, and explain 2 reasons why the speed of the blind increases throughout this raising cycle. So, what's happening there then? So as the blind rises, the roller diameter increases due to the thickness of the blind fabric. So it's getting bigger and bigger and bigger. Okay, so it's going to actually shift up quicker. As the blind rises, there's less weight hanging off the roller, meaning there's less load on the motor, so it's going to increase its speed a little bit. Any other valid suggestion? Other possible responses might include the motor must overcome the initial inertia of the system, so getting started, meaning the speed will significantly increase over the first couple of seconds of operation. So as it gets going, it's going to kick into life a little bit and go a bit faster. And that's that. Reduction ratio is simply the number of teeth on the worm wheel. For the worm wheel with 40 teeth can achieve a huge 40 to 1 speed reduction in a single stage. Okay, so the answer is 40 to 1. There's only one tooth on the worm itself. On the gear, you've got 40, so it's 40 to 1. Okay, if you didn't know that, it's 1 mark. A kind of sensible guess would have been my way forward on that one. The calculation, let me just check the question on this calculation. An alternative gear system used for the blind shown below shows a rack and pinion. So we've got the rack that goes up the side and the pinion that revolves around it. Try and get my hand going the right way. So it revolves it around it, gradually kind of working that way up or down. Okay. Calculate the distance moved by the rack, shown in figure 1.3. Explain why the pinion is not suitable for a blind system using your answer calculated above. So it's quite straightforward, this. Let's not overdo this one. So you do 12 times 3.7, which is 44.4. Let's just kind of look at why that is. We've got 12 teeth, and the gap between the teeth on the other one is 3.7 millimeters. So to roll over all of the 12, it's going to give us a rack. If you kind of open that gear out, it's going to give us a 44.4 millimeters, which is that kind of size. Now, if I put that in the background next to my window, where's my hand? There it is. You can see that's really not going to be very big, okay, compared to my window over here. There's the windowsill. There's 44 millimeters. So I've got to go kind of 2, 3, 4, 5, 6, 7, 8 times at least higher than that. Now, yeah, that bit of perspective there with my hand, but you get the kind of idea of what I'm saying. So, rotary to linear motion would not roll up the blind. Okay, so it's not the right kind of motion to roll the blind up. It's only a small distance being moved. Smoothness or any other possible answer. 1 mark for a correct answer, 1 mark for an explanation. Okay, so it's not moving far enough. The rack's not very big, 44 millimeters. The movement is not actually going to turn it, so it's not going to roll it round. So we're not going to get that roller blind rolling up on itself. So look at number 5. Okay, yeah. Figure 1.1 shows 3 views of a walkie-talkie. A walkie-talkie is a handheld portable two-way radio, a bit like a mobile phone. Yeah. So it's given us some sizes. It's given us lots of detail on there. So we've got the back view, the side view, the front view. Identify one smart or modern material that could be used in the design of the walkie-talkie. Justify how this smart or modern material would improve the design. So 2 marks. It's not a massive one, but we've got to know our materials and our differences of materials that we're talking about. So phosphorescent pigment, we talked about these. It reacts, smart material, it reacts to its environment, its external stimulus. Could be used to make the walkie-talkie glow in the dark. Okay, what advantage is that? Well, if we drop it when it's night time, you can see where it is. Biopolymers could be used in the case of the walkie-talkie, so at the end of the life it can degrade. It's going to create less environmental impact. So the natural kind of wearing down, the breaking up of it would be beneficial. LED or OLED screens could be used. It's then backlit. It's easy to read the numbers on the screen in the dark. ProCap or resistive touch screen would improve the user interface ease of use. Okay, so that resistive touch screen, so touch screen technology that we're used to on phones now. Any other valid? Okay, so polymers are not modern materials, so you can't just have plastics. 1 mark for justifying how this smart or modern material will be improving the design. Okay, one for naming it, 1 for improving it. Specific reference to the context in the question is needed for marks to be awarded. So you've got to say how it's going to help the user. Oh, right. Yeah, okay, the litter bin question. So figure 2.1 shows a waste paper basket where the sides are manufactured from expanded metal mesh. So you've got the kind of crisscrossy kind of metal mesh going on with a solid rim around the top and a solid bottom on the bottom. Identify 2 advantages of using expanded mesh rather than solid sheet for a waste paper basket. Let's have a look at the question, the mark scheme then. So it reduces costs as less material is needed in the manufacture. Okay, so you've got a kind of mesh rather than solid sheets. Reduces the weight. Imagine the weight difference. It's probably 20% of material rather than 100% material. Reduces the impact on the environment as less material is needed. Allows the user to see the waste paper so they know when it's full. Okay, it's really straightforward there. 1 mark for identifying an advantage of using expanded mesh rather than solid sheet. Reference to the correct context is needed again. If you're going to put something like cheap, it says it must be qualified. So why is it cheap? How does it make it cheap? How do we know it's cheap? Yeah, if you just put it's cheap, then that's no use. How can we increase the structural integrity then? The top rim and the bottom of the waste paper being a solid metal, 1 mark, helps stiffen the structure and maintain the shape, 1 mark, ensuring it can take impact from objects that are thrown in, 1 mark. The use of the diamond pattern allows for less material to be used, 1 mark, without losing too much strength, 1 mark, because of triangulation, 1 mark. Real straightforward, just explaining it in sentences. And I think that's where some of you kind of dropped down. You weren't giving it that A-level writing. It was still at GCSE level. There could be ribs or webs. Ribs are kind of little kind of bumps into it, okay, to give it extra strength underneath the base of the bin, which stiffen the material without increasing the material quantity. So if you get a sheet of paper, put it on your hand, it flops. If you roll the edges over, you're kind of increasing the structural rigidity of it. If you fold it or crease it in the middle as well, put some ribs or bumps in, it makes it a lot stiffer to use. Okay. That's that one. Question 7a. Yeah, the tennis racket. So modern tennis racket frames are commonly manufactured from aluminium alloy or composite materials. Figure 4.1 shows a tennis racket in use, if you didn't know what a tennis racket was. Figure 2 shows the front and side views of a tennis racket. Now, do we need that? No, not really. It just sets the scene. It gives us a visual of what we're talking about, so we're not going to make silly mistakes. Oh, he's come to have a look. There we go, back to sleep again. Compare the performance of a tennis racket made from aluminium alloy with the performance of a tennis racket made from a composite material. 2 marks, so quite straightforward this. The composite racket is likely to be lighter than aluminium racket, making it easier to hold and swing. There's 2 marks. Aluminium racket is likely to be less stiff than the composite racket, creating less shock or vibration to the user when in use. Composite racket is less likely to be dented or marked when in use, as the racket made from aluminium alloy is a soft metal or material. 2 marks. Composite racket can have reinforced sections added during the manufacture to improve strength and performance, whereas compared with aluminium racket would be adding weight. So it's just looking and thinking, so the composite is going to be made for that job rather than the aluminium, which is quite a lightweight material, but it's going to have issues with it again. Okay, and you can reduce that vibration. You know, if you know anything about racket sports, you can put little dampeners in there to reduce the vibrations. So finishes for the aluminium then. Anodizing is your basic one. It gives the racket a different colour, but it will not chip or peel when being continuously hit. So 1 mark for anodizing, 1 mark for the finish. It says 1 mark for identifying a suitable finish for a tennis racket frame made from aluminium alloy, electroplating, powder coating or paint to apply colour. 1 mark to justify why this is an appropriate finish to use. Specific reference to the context again is needed. Okay, so you could have painted it, an odd one there, electroplating, so you're putting a nicer finish over the top of it, anodizing your best one with aluminium. So how do we test it? Let me just check my question again, sorry. Explain 2 ways in physical testing could be used to test the functional feasibility of a tennis racket before full-scale commercial manufacture. So how are you going to test it to see whether it works before we actually manufacture this thing? Okay, whoops, clicked on the wrong one. Materials could be tested to determine the rate of corrosion when exposed to sun and rain. Okay, so put it outside, put it in the rain to test it. Materials could be exposed to different weather conditions, tested for a change in toughness. So we're kind of just constantly hitting a ball with it to see. Durability analysis of the racket to test the wear rate of the strings and the handle. Function tests through destructive testing to assess how a tennis racket will perform in normal use. User trials, so we can give it to some players, could be used to evaluate the performance of the racket when in use. Another mark. Up to 2 marks for explaining a way in which physical testing could be used to test the functional feasibility of a tennis racket before full-scale commercial manufacture. Okay, it says here, do not award marks for quality of communication checks throughout the production. Quality control, checks throughout the production. Specific reference to the context is needed. So nothing to do with checking it as it's before it's being made or as it's being made. What tests can we put into place? The bearing question, which was, if I remember right, is the gates for going through to the train station. Explain 2 reasons why bearings would be used in a mechanical gate system. So you're looking here for the thing that makes the arm move backwards and forwards. That's called a bearing, that allows the kind of smooth movement of something. Okay, so if we go on to the the mark scheme, a bearing is a component which supports a moving part and allows it to move only in desired motion. Okay, so 1 mark for each there, with little friction. Okay, so a bearing, smooth movement, so in your wheels on your bike, skateboards, scooters, that kind of thing. Most commonly used to support a drive shaft so it can rotate freely. So if you've got something driving it and turning around like that, you want it to have a bearing around it so it rotates in there and keeps that rotation nice and smooth. And that, I think, is that. So not a real difficult question paper, it's just looking at the complexity of your answers, the kind of depth of your answers you put in, and knowing your materials. The smart materials was a particularly weak one, and knowing that, and that impacted 2 questions. Okay, because a lot of people just talked about ABS for the walkie-talkie, and that's not right. We were looking for a smart material and how that could be used. Okay, hope this helps. I hope you kind of appreciate what's gone in, and I'm trying different things. Let me know if you want anything done differently. Like the page, subscribe. Apparently 1 million views, and I can get a gold YouTube button. So that's clearly what I'm after. All right, take care, guys. Thank you. Bye.